Greetings, everyone. This is Group CSJ5 2025, and our project title is a smart IoT and machine learning model for real-time water quality monitoring with automated pump control. My name is Nakanjako Tedishila, and my group mates are Emmanuel Kenny Samuel, Shima Joshua. Yeah, the background for our project. So National Water and Sewage Corporation Massachusetts Water Treatment Plant treats 30 million liters per day for Eastern Uganda, yet monitors water quality manually. And that is only 3 times per 8-hour shift. There is no real-time alert, no automated response. So Lake Victoria being the sole source, it faces rapid and unpredictable pollution from urban runoff, agriculture, and industrial discharge. Sometimes there can be nighttime contamination that can go undetected for hours. This creates a gap between our project, this creates a gap between the existing projects and then our project. And the gaps include no IoT sensors, no automated pump shutdown, no remote monitoring, because their results, they have paper-based reports. These don't allow trend analysis. And also waterborne diseases remain a threat. Then we go to the literature for our project. Prior literature shows that IoT sensors improve water monitoring over manual methods. That is Pasika and Gandler 2020. Then also what prior work shows is that machine learning achieves high accuracy in water quality classification. That's Shafi 2024. Then also cloud and mobile platforms enable remote access to real-time data. And then also long range and GSM improve reliability in remote IoT environments. So what is missing with these already existing works? Most systems focus on data collection only, no automated pump level control. Then also lab-tested models lack real-world deployment in live treatment facilities. There is no unified framework integrating real-time alerts plus machine learning and automated pump shutdown. And also there is limited integration of multiple communication modes, for example, Wi-Fi and GSM for fault tolerance. For our problem statement, National Water and Sewage Corporation Massachusetts monitors water quality manually. That is 3 times per 8-hour shift with no automated detection or shutdown mechanism. Contamination events can persist undetected for up to 8 hours, putting hundreds of thousands of consumers at risk. So our main objective was to design and implement a smart IoT and machine learning model for continuous real-time water quality monitoring and automated pump control at the National Water Masese Water Treatment Plant in Jinja. So we divided our specific objectives into 4, that is IoT monitoring system, and that was to design and implement an IoT-based water quality monitoring system that is integrated with an ESP32 microcontroller and automated pump actuator. And the next was to build a cross-platform Flutter mobile application for real-time monitoring, pump status tracking, and SMS alert notification. Then the third one was to develop a real-time automated pump control mechanism that prevents unsafe water distribution under abnormal water quality conditions. And then lastly was to develop a cloud-based data management system using Spark-based PostgreSQL for storing, processing, and visualizing real-time water quality data.
This is Shima Joshua, and I'm going to be going through this the methodology. So the development system consists of a three-layer architecture that has the perception layer, network layer, and application layer. So for the perception layer, it handles data collection and automated pump control using the ESP32 microcontroller. Then the network layer manages data transmission through Wi-Fi and GSM communication modules. Then the application layer handles cloud storage, machine learning, pre-processing alerts, and then reporting and um, real-time monitoring through the Flutter mobile application. So we use the Agile iterative system development lifecycle, whereby we also had sprints. We gathered requirements, hardware, software, and then integration testing. So we also conducted a field study from National Water and Sewerage Corporation, Masese. Um, yeah. So for the data set, it consisted of 10,001 water quality records that included the water quality parameters usually measured. There is pH, hardness, solids, sulfide, conductivity, among others. So our target was for us to classify whether the water is safe to drink, which is potability, or non-safe to consume, which is non-potable. We also use the synthetic minority oversampling technique, which is the SMOT, to address class imbalance. So after the models were trained, we evaluated that the random forest and the XGBoost were among the best performing models. So for this image shows the SMOT balance before and after carrying out the um, synthetic minority oversampling technique. So as it is shown here, this image illustrates the dataset class distribution before and after synthetic minority oversampling technique balancing. So for the confusion matrix analyzes the classification performance of the evaluated machine learning model after smart preprocessing. So the results, they clearly show the number of correctly classified safe, unsafe water samples together with false positives and false negative. So this enables like performance comparison between different classification models. So for the tools that we used the hardware. We used the ESP32 microcontroller, the pH total dissolved solids, TDS, turbidity sensors, EC and temperature sensors. Then for the software, we used C++ as the Arduino IDE environment for programming the logic of these sensors. We used also the ESP32 firmware, Flutter, Supabase, and then GitHub for version control. So for the testing, each sensor and module, we tested them independently. So we carried out 15 test cases across conditions, and in all 15 test cases, it was declared pass. So for the random forest, as I said, was the best performing model with an 84.90% accuracy, F1 score of 84.47, precision, and then recall. So these are receiver operating curves for all models. This figure shows the receiver operating curves for all models after the synthetic minority oversampling technique. So for the results, like I said, we tested 15 test cases scenario whereby if the water is safe to consume, the pump turns itself on, and if it is unsafe, the pump is off, and then if there is a fault in the system, the system triggers a fail-safe mode. So for the test cases, we tested water quality parameters as shown here. So we have test numbers, and then we have pH, TDS, electrical conductivity, turbidity, and then we classify the state of the water, if it is safe or unsafe to consume. Yeah, so this was it for the methodology. Thank you.
This is Emmanuel Kenye Samuel, the third member of the group. I'll be taking us through the system implementation. So the implementation of the system, it started. So after the data collection, we performed data pre-processing to improve actually the quality of the data set. Like this involved handling missing values, cleaning inconsistencies, records, when analyzing the data, and then conducting explanatory analysis and understanding the relationships between the different parameters. Then we moved on to develop and evaluate several machine learning algorithms that include the random forest, XGBoost, AdaBoost, logic regression, and the rest. So on the data set, we divided it into two. One which is the training data set, and then the other one is the testing data set. And the models were evaluated based on the accuracy, precision call, and F1 score matrices. So from our training and evaluation of the results, random forest actually achieved the highest performance with 84.9, and then the F1 score. So looking at the diagram on the screen, that's actually how our model is set up. So you can see like there are two tanks. One is a reservoir tank, and there's the other tank where like the testing is actually done. That's where our sensors are. So what happens is actually like how the machine learning model is integrated into the whole app and into the machine learning. So the ESP32 accesses the microcontroller. So what happens is water is first tested in tank A, where the sensors are located. So what happens is the water is tested, the data is sent into our Superbase database via the ESP32. So then after it's sent to the database, the machine learning module is run against it, then it predicts whether it's safe or unsafe. So then inside in the diagram we have a relay model which acts as a switch, like when water is tested and we found that the parameters are out of range. So like all the parameters have their ranges within which it is considered safe, and then other than that it's considered unsafe for drinking. So the water moves on to the, so when water is clean, it is pumped using the pump into the reservoir tank. But when water is not safe, what happens is it's automatically turned off using the relay model. So our hardware implementation, we included a pH and turbidity data sensor with the controller. Then we implemented the Superbase, that is for our data set. In addition, we developed a Flutter app. So you can see from the diagram there. You can move on to the next slide, please. So there you can see the Flutter mobile application. So those are like screenshots of the few pages that we have. We have the dashboard. We have the one for history and charts. Then we have a small chat board there where a user can ask for communications. So the key innovation of this system is actually the automated pump mechanism. When the machine learning model detects unsafe water conditions, the relay automatically switches off the pump and sends an alert notification to the operator. This prevents like contaminated water from reaching the distribution reservoir and enables like and alerts are sent to the respective officers, then they're able to now come back. So the system was then tested like using unit testing, integrating testing. You can move on to the next slide, please. So they are looking at our key findings. So like I said before, the random model was the best performing model with 84.9%. So the sensor data is sent on the app after every 30 seconds, so meaning water is monitored after every 30 seconds. Then also we did some tests of which 15 out of 15 sensor test cases passed. Then it is on 3 layer, and then the 8-hour gap has been reduced to 0. You can move on to the next page, please. Then discussing of the system and ML results, one looking at the system performance. One is the continuous real-time monitoring achieved across all test scenarios. That is seen from the 15 tests done. The sensor reading are transmitted reliably to the supervisor via Wi-Fi connection with no delays in communication. The automated pump responded like correctly actually does. Like when we test, like you add salt into the water to change its like total dissolved solid to actually work. Then the Flutter mobile app actually did the real-time readings and all that. Then we use the SMOT for balancing like the data because we found that the save water in the data set was less than. Then we look at the performance, the X boot. So we had the Rico curve, the smart and all that. Move on to the next page. So discussing the limitations and recommendations. One of the limitations, like when we went on the field, whatever, like the officers wanted to monitor heavy water, heavy metals, of which we don't have in our system. So like the sensors periodically, like they need recalibration. Then we tested a limited monitoring points. Then the ML model can be improved like with a larger data set because with that data set is small. Then future work, we can categorize into immediate short-term and long-term. We improve sensor calibration, expand functionality. Then short-term add heavy metal like sensors to determine like heavy metals to detect it. Then maybe long-term use deep learning for anomaly detection and all that. You can go on to the next page. Then discussing the achievements. So one of our objectives was to design and implement monitoring system with DSP that do with automated pump, of which we successfully implemented, as shown in the diagram. Then the next one was to develop an automated pump control for unsafe water, of which it functioned correctly. Then the Flutter publication enabled us in sending alerts, allowing us to check the history and see actually the data in real time. Then the cloud-based management system, which is a super base, also helped us in the data. We can go to the next page. Then in conclusion, like this project of ours actually successfully demonstrated that combining like the various IoT sensors with machine learning, cloud computing, and mobile app can replace manual 8-hour monitoring cycles. So automated intelligence and water quality. You can go to the next. So this is the end of it, but